the last few years to really make reinforcement learning more mature, closer to the real world, and deployed intelligent applications. He has worked on many topics related to that, on deep reinforcement learning, on motor planning, on planning of trajectories of robots, and also on the fundamental algorithms which underpin reinforcement learning. And he's going to speak today on one of these algorithms, on the policy gradient methods. So thanks, John. Over to you.
Thanks for the very nice introduction, Sebastian. So I wish I could be out there in Cambridge with you and participate in the summer school, but unfortunately I'm not very good with jet lag, so I decided to stay home for this one. So this tutorial is going to be a policy gradient tutorial, which is closely related to the tutorial that Peter Abil and I gave at NIPS this last year, but with some modifications. And it's actually going to be fairly basic and just introduce the basics of policy gradients, evolution strategies, natural policy gradient. But actually, I think the basics go a really long way for these algorithms. So, so I hope it's beneficial for all of you. So before I get into the details of some of these algorithms that I'm going to talk about, I'll go. I want to just put them in context a little bit with the other algorithms from deep reinforcement learning. So deep reinforcement learning is just reinforcement learning where you're using neural networks as your function approximators. And the one interesting thing is that in reinforcement learning, there are several different choices of what to approximate. So this contrasts with, say, supervised learning, where you just want to approximate your conditional probability distribution or something like that. So in reinforcement learning, there are several reasonable choices. You could try to approximate a policy, which is your function that chooses the next action. You could try to approximate a value function, which is a function that tells you how good a certain state is or a certain state action pair is. Or you could try to learn the dynamics model, which predicts the next state and the reward, which you would then plug into a planning algorithm. So here in this talk, I'm going to focus on learning policies, and but I would say that there's sort of a taxonomy of different methods that sort of live in this space. So on the one hand, you can directly optimize policies, and one way to do that is with derivative-free optimization, or also known as evolutionary algorithms, where you just you try to optimize over the parameter vector without using anything about the actual trajectories generated from that parameter vector. So you're just treating the whole environment as a black box where you put in a parameter vector and you get a return. Then there are these policy gradient methods which actually take advantage of the temporal structure of the problem and try to figure out which are the good actions and which are the bad actions. And let's make the good actions more probable. Let's adjust our actions so that they're better. So that's sort of what we've got on the policy optimization side. And dynamic programming is another class of algorithms that are based on learning value functions. And in the so there's a set of classic algorithms that will exactly solve an MDP, where you have access to all of the information about the transition probabilities and the reward function. So there's these algorithms that you might have learned about in an elementary course of policy iteration and value iteration, which will exactly solve for the optimal policy and the value function for an MDP. And it's possible to come up with approximate versions of these algorithms. So that's another class of methods there. And Q-learning is sort of an approximate version of, or DQN, deep Q-learning is sort of an approximate version of value iteration. But we're going to focus here on, in this talk, I'm going to focus on the policy optimization methods. And well, first, what's the difference between them? In empirically and and also sort of conceptually. Well, the one big advantage of the policy optimization methods is you're optimizing the thing you care about, which is the expected return of the policy. In contrast, the dynamic programming methods are more indirect. They try to exploit the problem structure to learn a value function using a self-consistency property that the value function should have. Specifically, that the value function now should be consistent with the value function at the next time step. So they can be, so there's a slight mismatch between what's in your loss function, which is this error of the self-consistency condition, and what you actually care about, which is the expected return. But empirically, what happens is the policy optimization methods are a bit more versatile, meaning they tend to work in more situations, whereas the dynamic programming methods are more sample efficient when they do work. This is just a very rough assessment of the empirical results, and the jury's still out on which methods are going to work the best in the long run, but this is just the current state of things. And also the policy optimization methods are more compatible with richer function approximators, such as recurrent neural networks, and also architectures that add auxiliary objectives, such as making predictions in addition to control. So that's sort of that's the advantage of the policy optimization methods, whereas the dynamic programming methods are more compatible with off-policy learning, and in turn that makes them more compatible with exploration, because to do exploration, you often want to collect data from a policy that other than the one that's your current best guess of the optimal policy. Okay, so that's just an overview of where policy optimization methods sit relative to the other methods. But now I'm going to get more into the details and set up what the problem is more precisely. So we're going to be concerned with parameterized policies, and what that means is you have a policy, a family of policies that's indexed with some parameter vector, which in this case is just a vector of real numbers. And this could either be a deterministic policy where the action is a deterministic function of the state and the parameter vector, or you could have a stochastic policy where you have a condition where the action is a conditional probability distribution that depends on the state and the parameter vector. And this is totally analogous to classification or regression, where the state is your input and the action is your output. And you can use the exact same kind of function approximators that you would use in classification or regression. For example, if your reinforcement learning problem has a discrete action space, you can take a network architecture that would have been used for classification, where your network outputs a vector of probabilities. Whereas if you have a continuous action space, you can use a network that you would have used for regression, where the network can be interpreted as outputting a mean and a diagonal covariance matrix for a Gaussian. Also, for the purposes of this talk, we're going to be concerned with the episodic reinforcement learning setting. There are actually several different ways you can set up the optimization problem, and when it comes down to the algorithms, it actually doesn't matter that much, since the algorithms look basically the same. But we're going to be most concerned with what's called the episodic setting, where we have an agent whose experience is broken up into a series of episodes, each of which has a finite number of time steps. So in each episode, you sample an initial state from some distribution mu, and the agent acts until it reaches a certain terminal state, at which point the episode ends. Just to give a few examples of what an episode might look like, let's say you have a taxi robot and the episode ends when it reaches its destination. So then termination is good and we want the episode to terminate as fast as possible. You might also have a situation where the episode has a fixed length and you just try to accumulate as much reward as possible during that fixed amount of time. So that would be like a waiter robot finishing where the episode ends when it finishes its shift. Or you could have another kind of MDP where you want the episode to be as long as possible. Like you have a walking robot and you want it to be able to stand up as long as possible or stay up as long as possible before falling over. So the goal in this setting is to maximize the expected reward per episode. So we're going to use capital R to denote the return, which is to be distinguished from the reward, so the reward corresponds to a single time step, where the return corresponds to a whole episode. So reward will be lowercase r and return is capital R. And we're concerned with maximizing the expected reward that you get, the expected return, which is the sum of reward and the whole episode. So there are various ways of optimizing this expected return. And first, I'm going to talk about what's sort of conceptually the simplest way to do it, which is with derivative-free optimization. And the idea here is you put in a parameter, you have your parameter vector, which defines your policy, and you treat everything else as a black box. So actually what's happening inside the black box is there's a series of time steps, and each time step you're sampling an action and then generating next state and reward. But we're going to ignore all of that and just say we put the parameter into that black box, get a return, which is stochastic, and use that information to try to adjust our parameter vector. So first I'm going to just introduce an algorithm called the cross-entropy method, which is simple to understand intuitively. And that'll give you an intuition for what's kind of going on in these derivative-free optimization methods. And then I'll talk a little bit more about how to justify it. But first, just to introduce the algorithm, the main state is here, meaning our current estimate about the parameter vector, the optimal parameters, is stored in two vectors. We have a vector, a mean, and a standard deviation for each parameter. That means we have a Gaussian with diagonal covariance over parameters. And what we're going to do is iteratively improve this distribution over parameters. So each iteration, what we do is first we collect n samples, n random parameters by sampling from this Gaussian distribution. Then for each parameter vector, we perform one episode with it. That means we just run our policy for one episode until the episode terminates. And that gives us a return. That's a typo, I should say return, capital R. Then after we've done these n episodes, we take the top p%, where p is a hyperparameter of this algorithm. We take the top p%, like the top 20%, which now we fit a new Gaussian distribution to the elite set and update mu and sigma. So fitting it, that just means usually we do maximum likelihood on that elite set. So this, if you are familiar with evolutionary algorithms, this will be a kind of familiar structure where you have a certain population which is defined by a Gaussian distribution, and then you pick the members of the population that have highest fitness, and you fit a new distribution to those highly fit members of the population, and then you repeat the process again. So it sort of makes sense that you're just moving your distribution towards the good parts of parameter space over time. And so you keep doing this for a while, and then at the very end, after you've done all of your iterations, you return the final mean parameter, which is your best estimate for the optimal parameter. So this simple algorithm is called it's called the cross-entropy method for sort of historical reasons, which is that it's related to it's actually a method. It was derived for something else, for integral estimation, but actually I won't go into the details for that. But the funny thing is sometimes this algorithm works embarrassingly well, and in particular, there's so the game of Tetris has for a long time been a benchmark task in reinforcement learning, or in approximate dynamic programming, which sort of means the same thing as reinforcement learning. And so a lot of so this table is taken from the paper Learning Tetris using the noisy cross-entropy method, and it shows that there were several previous papers that used reinforcement learning techniques to play Tetris, and they got certain scores that are in the low thousands. And but then so it turns out the best performance is obtained by this hand-coded policy or by genetic algorithms, and as it turns, both of which there's a lot of hand engineering in both of these cases. And the paper that this table is taken from showed that if you just use the cross-entropy method, you get a really high score, which is competitive with the best performance obtained by these kind of handcrafted methods. And you get much better results than any of the reinforcement learning methods. And I think so in particular, methods that are based on policy iteration and policy gradients. So these are those, when I say reinforcement learning methods, I mean methods that exploit the fact that you're trying to solve an MTP and try to take advantage of the temporal structure of the problem. So I think the reason why this happens is because cross-entropy method is optimizing, well, mostly optimizing the right thing, which is the performance of the parameter vector over many thousands of time steps that it takes in an episode. Whereas the reinforcement learning methods have to make some approximations. So even though they're exploiting the structure of the problem, they end up optimizing the wrong thing. In particular, they have to introduce what's called a discount factor, where you sort of ignore long-term dependencies, and I think that's probably what kills them. But you don't need to worry about a discount factor with the cross-entropy method. I'm going to talk about the discount factor shortly. So anyway, a few years ago, there was a paper showing that by being really careful about how you approximate your value function, you actually can get good results on Tetris using approximate dynamic programming. But I still think it's sort of a win for cross-entropy because of how simple the algorithm is and how it works pretty well without that much tuning. So I didn't really justify the cross-entropy method, though it sort of makes sense intuitively. But now I'm going to talk about a very closely related approach, which can be mathematically derived pretty straightforwardly, which is to do stochastic gradient descent on the parameters of your distribution. And shortly, I'll show how cross-entropy method is closely related to this shortly. But so the idea here is in cross-entropy method, we had this Gaussian distribution, and we're iteratively moving this Gaussian distribution to give better and better returns. So can we just do stochastic gradient descent, or stochastic gradient ascent on these distribution parameters? So that's what we're going to do here. And let's say that we define this, we use this distribution P sub mu over our policy parameters. So in this case, mu, mu could be the mean of the Gaussian, or it could be the mean and the standard deviation. Let's pretend for now we're just optimizing over the mean, and we have a fixed standard deviation. And the same method can be used to adjust the standard deviation, but usually that's not very useful anyway. So let's just say we're optimizing over the mean of a Gaussian distribution. So the return depends on the policy parameter and some noise. So let's just say we've defined everything so that the return is a deterministic function of the parameter vector theta and some noise zeta. So now our optimization problem can be written like follows. We're maximizing over mu of the expectation of our return, where reward is, where the parameter theta is sampled according to this distribution. Well, this is a little bit non-straightforward because our return is unknown and it's possibly non-differentiable. So we don't know this function r, and it's probably not a nice and smooth function of the parameter vector theta. So, especially, let's say we have just a discrete action space, then clearly r isn't going to be a deterministic function of our policy parameter. So, so it's kind of non-obvious that we can even do this, or that we can even differentiate this, but as it turns out, we can. And it's a very basic and important technique called the score function gradient estimator, also known as the likelihood ratio gradient estimator. And the way it looks is the gradient of this expectation equals the expectation of grad log probability times return. So, so we've just, what we've done here is we've just, the idea of a gradient estimator is you want to get, you're trying to estimate the gradient of this expectation, and we want to write that as an expectation of something, which we can then compute, we can get a Monte Carlo estimate of. So here we can get our Monte Carlo estimate by just collecting a bunch of samples, and then for each sample we take grad log probability times return, and we take the empirical average of those. Okay, so I'll derive this in a sec, but before I derive that, let's just look at the relationship between this score function gradient estimator and what we were doing in the cross-entropy method. So here, score function gradient estimator, we've got grad log probability times return. Whereas in the cross-entropy method, we have an objective that we optimize each iteration. I actually didn't write this in the algorithm, the pseudocode, but the way we fit the Gaussian distribution to our data points is we do maximum likelihood, or we maximize the log probability of our elite set under the parameterized distribution. So what that means is, so what we have here is if we look at all of our samples, not just the elite set, what we have is log probability of the sample times some function of the return. And in this case, what we did in the cross-entropy method is we just took the indicator that return r was above threshold. So it's either 0 or 1. And so you can see that if we got rid of this thresholding function f, then the objective we're maximizing in each batch, in each iteration of cross-entropy is the same as the objective we've differentiated with the score function gradient estimator. So you can see that they're going to do similar updates, but maybe the cross-entropy method will be able to take a bigger step each iteration because you don't have to just take a single gradient step. Actually, another illuminating connection is between the score function gradient estimator and between doing finite differences. So it turns out that the score function gradient estimator is very similar to doing towards another kind of intuitive algorithm that involves taking a random direction and doing a directional derivative in that direction, and then doing a gradient step using that directional derivative. So I'll show you that the score function gradient estimator comes out to be almost the same as a certain kind of direction finite difference. So to see that, let's just compute explicitly what happens with our score function gradient estimator in the Gaussian case, where we're optimizing over the mean of the Gaussian. So here's our log probability, and then we take the gradient of the log probability. So it's just parameter minus mean over standard deviation squared. And then, so here's our estimator, reward times the parameter minus the mean. Okay, so it doesn't look so illuminating yet. But now, let's say we do antithetic sampling. So if you have a symmetric distribution, such as a Gaussian, you can compute your expectation. You can get the same expectation by collecting two samples at a time, where you collect a random sample from your distribution, and then the negative of that sample, or the mirror image of that sample around the center of this distribution. So this is just a general kind of Monte Carlo estimation technique called antithetic sampling. So here, what we do, each step we take a pair of samples, mean plus noise times noise times standard deviation, and mean minus noise times standard deviation. Here, Z is from normal 0, 1, meaning mean 0, standard deviation. I mean, variance is the identity. And sigma is, this is our vector of standard deviations. So this is an element-wise product. Or you can just consider the scalar case for now, if you don't want to worry about vectors. So anyway, if we write what we're going to do here is write down the score function gradient estimator, but where you use antithetic sampling. So you got two samples at a time. So writing an average for two samples, we have reward at one sample, return at one sample minus return at the other sample, times our Z, which is our noise, which is just normal 0, 1. So so what we have here is we have Z is effectively just a random direction because we just sampled a random vector, and then we look at the return measured at like mean plus Z and mean minus Z, scaled appropriately. So we have so this is just our finite difference, and we're dividing by the the length or the size of the perturbation, sigma. So here, this is just our directional derivative, and then we're multiplying it by the random direction that the derivative is taken in. So, so this is a kind of intuitive algorithm, sometimes called Siamese perturbation stochastic approximation. It's not exactly, I don't know, I don't want to get into specifics of that, but this is a kind of intuitive algorithm, and you can see that it's exactly what you get by doing the score function gradient estimator with antithetic sampling. Oh yeah, so if you use different noise samples to do both function evaluations, then you could potentially have a lot of variance because it could be that most of the difference between these returns is coming from the noise, and it's not coming from the difference in parameter. So you end up having an error term that goes like 1 over sigma. So if you have a very small sigma and you use two different noise samples, then you're gonna get a pretty bad estimate. But if you use the same noise samples, so if zeta equals zeta prime here, then you get a much better estimate, because what happens is you're under almost all conditions, these two terms are going to be positively correlated. Meaning when you take an expectation over zeta, these terms are going to be very positively correlated. So if we take the difference of them, we're going to cancel out some of the noise that comes from zeta. So anyway, we get much lower variance if we're able to freeze the noise, and so we can if we have access to a simulator, for example, then we can use the same random seed and evaluate two different parameter vectors for that random seed. Of course, if it's in the real world, we can't do that. Okay, so that's basically that's sort of three different views on derivative-free optimization, and we have these kind of similar algorithms that we get. I'll just quickly show how you derive the score function gradient estimator in case you haven't seen this before. So this is the estimator that I wrote on the previous slide. So you can just derive it by writing the expectation as an integral, and then you just swap the integral and the gradient, and you can do that whenever the probability distribution is continuous. Actually, it doesn't even have to be differentiable. It just has to be almost everywhere differentiable. So as long as it's almost everywhere differentiable, you can swap this integral and the derivative, and then you get this. So then what you have to do is you use, so by the chain rule, when you take grad log probability, that's equal to grad probability divided by probability. What we've done here, going from equation 2 to equation 3 here, is we've just multiplied and divided by the probability density, and then we pull the so then the reason we did that is so we can turn the integral back into an expectation, because we need to have some probability measure multiplying the integrand. So we turn it back into an expectation, and now we get this expectation of grad log probability times return. So that's that's my overview on the derivative-free optimization. There are several different versions of this which are kind of which are very similar. So actually, the algorithm where you do random direction finite differences, and you do stochastic gradient ascent with that, is usually called evolution strategies, and this is from the 70s, and it's also related to this SPSA algorithm. So Kress entropy method has become pretty popular for applications where you have a fairly small number of parameters, and there's actually another version of it which is even more popular, called covariance matrix adaptation, where instead of using a diagonal covariance, you use a full covariance matrix, but there are also some other tricks which help out to get a better estimate of this full matrix, because otherwise you wouldn't be able to estimate it from a single batch. So CMA, covariance matrix adaptation, is a way of iteratively updating your full covariance matrix. And this is very effective in a lot of problems where you have a fairly small number of parameters. These are also pretty closely related to some algorithms that are more that have been more focused on the robotics or reinforcement learning setting, which are reward-weighted regression and the power algorithms. So CMA has actually been very popular and successful for optimizing locomotion controllers for simulated robots, and also a little bit for real robots, but I won't go into that. So, for example, there's this long-running challenge of playing soccer, robot soccer, which is done in simulation and in the real world. But the leading teams in simulation, in the simulation league, what they do is they optimize a bunch of controllers for walking and for getting up off the ground by first they parameterize this controller. So they have some kind of 20 parameter thing which is like a trajectory which is going to be followed with PID, where you have to tune a bunch of targets and gains for PID controllers. So they parameterize this thing, some kind of trajectory, and then they use CMA to optimize over the parameters. And they do this for walking and getting up and so on. So, and then they use CMA to optimize this parameter. And it's also used for optimizing locomotion controllers more in the context of computer graphics, where you're trying to get physically realistic walking controllers. So it's been quite successful in this kind of application. recently there's a recent paper showing that evolution strategies performs pretty well on the Atari benchmark, which has been used for deep reinforcement learning. So the previously Q-learning and policy gradient methods has been shown to do well on Atari, and Solomons et al. Showed that if you just use evolution strategies using the same kind of network which was used for policy gradients, it actually gives competitive performance. It might be a little bit worse in terms of sample complexity, but actually, well, it's much easier to parallelize. So, and yeah, so it might have advantages in some cases, and it's also not as sensitive to certain. It doesn't require as many sort of approximations as policy gradient methods, where you have to worry about like frame skip, as it's called, where you have to repeat actions for multiple frames. Otherwise, it doesn't learn very well. And policy gradient methods, you also have to worry about, you have to introduce discount factors. So the nice thing about evolution strategies is, or the black box optimization approach is, you don't have to worry about the time horizon as much. You don't have to worry about what's called credit assignment, where you're trying to figure out which actions were responsible for the rewards, since you're just directly optimizing in parameter space. Okay, so that's it for evolution strategies. I would stop for questions, but I'm not sure if it's going to work very well because I can't see everyone, and I'm not sure if your mic, their microphones. I'm not sure if I'd be able to hear you. Okay, yeah. Then I'll just open it up if anyone has any questions before we go on to the next section.
All right, I think we are ready to go to the next section.
Okay, ready for the next section, great. Okay, so on to policy gradient methods. Okay, so the problem we're trying to solve, again, is to optimize the expected reward of expected return of a parameterized policy. And what we're going to do here in the for policy gradient methods is we're going to have a policy parameter theta, which is fixed at any given point in the algorithm, and we update it over time. But instead of keeping track of a distribution over policy parameters, we're going to have a single policy parameter at any given time, and we're going to estimate the gradient of this expectation with respect to the policy parameter. So one way to think about this is now our noise is in action space instead of in parameter space. The intuition of what we're going to do is we collect a bunch of trajectories using our parameterized policy, and well, there are three different ways of thinking of it, which are all correct and correspond to slightly different kinds of methods. One is we try to make the good trajectories more probable. If we do that, we don't have to worry about the individual actions. We just have a whole trajectory, and we're trying to make the good ones more probable and the bad ones less probable. Okay, then what we can try to do to get better policy gradient estimates is figure out which actions were good and which ones were bad. And then we try to make the good actions more probable and the bad actions less probable. And then there's a third class of methods which actually try to, if you have, these only really make sense if you have a continuous action space. And these methods will try to push your actions towards slightly better actions. So you try to estimate these require some kind of value function, which will tell you how good a given action is, and it'll push that towards a better action. So I don't think I'm going to have time to get into those, but that's another interesting class of methods. So now I'll get into how you actually do that mathematically. And the way it works is to just, we're going to use the same kind of score function gradient estimator that we used in the derivative-free optimization setting. Except now our random variable, instead of being a policy parameter, is the whole trajectory. I mean, remember how I said that the noise now is in action space or trajectory space rather than parameter space. So now our random variable is the whole trajectory. If we just go through the motions to derive the score function estimator, we get a perfectly good estimator here, which says that the gradient of the expected return is just the expectation of grad log probability of the trajectory times the return of the trajectory, which is just, recall, our return is just the sum of rewards. Okay, that's not so useful by itself because we've got this probability of a whole trajectory. And by the way, it's worth talking at this point about which variables or which quantities are assumed to be known and which ones are not known when we're trying to run our algorithm. So which parts, so for example, I mean, you have to assume, I've just written down this optimization problem, but I haven't said anything about which, whether we know what the MDP parameters are and so on. So do we know what the transition probabilities are, and do we know what the reward function is? Or are these things quantities that we have to estimate? So we're going to be interested here in the setting that we don't know what the transition probabilities are, and we don't know what the reward function is. And but we have to learn anyway. So our learning algorithm has to either learn these quantities or somehow just learn the policy without having access to those quantities. So actually, it's worth just appreciating that, well, this is kind of non-trivial, that even if you have this problem with all sorts of unknown quantities, that we can still optimize a policy for it, even though we don't know what the dynamics model is, which sits inside of this expectation, because it determines what our trajectories are going to be. So it's just worth noting that this is quite different from the regime we're in with other kinds of most other machine learning problems, not bandit problems. So bandit problems, you assume you have this unknown distribution of returns from the different arms. But something like supervised learning, usually you have a finite set of training data, but given your training data, you have analytic access to the objective you're trying to maximize. So you can compute gradients of your objective and even second derivatives and so on. But here, we don't have access to the whole objective. We don't have analytic access to this expectation that we're trying to optimize. It has quantities in it that we don't know. So when we write out the probability of the trajectory, we can just use the chain rule probabilities to write it as a product of the probability of the initial state, mu of S naught, times the product over time of probability of action times probability of next state and reward. So, okay, so we know the probability, we have access to this part, the probability of action given state and parameter vector, because the policy is part of our agent. This is what we're learning. So we can take derivatives and so forth of this, but we don't know what the transition probabilities are, and we don't know what the initial state distribution is. So that would be trouble if we were just trying to. That's going to cause trouble if we wanted to somehow analytically evaluate this expectation. But we could, of course, do Monte Carlo estimates of it, and that's what we have to do. So okay, so when we take the log of this probability, it turns the product into a sum, and then we take the gradient of this log probability, and now all of the terms that don't depend on theta drop out of this expression. So that's nice because all of the terms that we don't know just disappeared. And then we're left with, then just plugging that back into our estimator formula, we get the following. We have expectation over trajectories of return times the gradient of the sum of log probabilities. So, so this formula, okay, so let's just look at this formula for a second. This formula means that so you can get a Monte Carlo estimate of the expected return by taking a bunch of trajectories, generating a bunch of trajectories, and then for each one, we take the return of that trajectory, and then we take the grad log probability of all the actions along those trajectories, and we multiply return times grad log probability. And that gives us our empirical estimate of the policy gradient. And the interpretation is sometimes we're going to get a high return, sometimes we're going to get a low return. We want to maximize the log probability of the samples that have a high return. So we're going to move our distribution over to put more probability mass on those samples, or probability density on those samples. Okay, so that's the most crude kind of gradient estimator we can get. What we can do now is try to derive lower variance gradient estimators. So we're going to get this, an estimator that has the same mean, but it's going to have lower variance. So it's going to be a better estimator, and it's going to require fewer samples to get a good estimate. So the way we do that is we can run through the exact same argument to get the gradient estimator for a single reward term. So in the previous slide, we were trying to get the grad expectation of the sum of rewards. Now we're just going to get grad expectation of a single reward. So grad expectation of this r sub t prime. So just doing the motions, we get that it's equal to r sub t prime times the sum of grad log probabilities of the preceding actions. Because the past action, the past actions aren't going to affect this reward at all. So we don't need to worry about the subsequent actions. Okay, so then we want to get the grad expectation of the sum of rewards, capital R. So we just sum this formula over t prime. Sorry, I said sum it over t. I meant sum it over t prime. So, okay, so that leaves us, so you just do the bookkeeping there, and what we get is the sum of reward sub t prime times the sum of grad log probability of preceding actions, or you can rearrange it to be grad log probability times sum of the rewards after that action. So sum of following rewards. So the interpretation of this formula is if you get a high reward, that means that your preceding actions were good, so you should make them more probable. This formula says that if for a given action, if the sum of following rewards were high, then we should increase the probability of that action. And these formulas, it's just a trivial rearrangement of the sum. It's just bookkeeping to switch between these two formulas. So this is a better estimate of the policy gradient, which respects causality. Now we can reduce the variance. So the name of the game is variance reduction, because the policy gradient is what we care about. Now we just want to get estimated as well as possible, as fast as possible, which means reducing the variance as much as possible of our estimator. So the best variance, one really good variance reduction technique is to introduce what's called a baseline. So the intuition behind the baseline is, in our previous formula, let's look at the last formula. We've got grad log probability of the actions times the sum of following rewards. So if we make an empirical estimate of this, we're going to adjust the probability of every single action we performed in our sample trajectories to try to increase it. let me say that again. So we collect a bunch of trajectories, then we plug those trajectories into this formula. And so that means we take grad log probability of each action times the sum of following rewards. And we take that gradient ascent step. So that means we're increasing the probability of, and let's say all of our rewards are positive. Let's just suppose they're positive in a certain problem. Then our gradient ascent step is going to try to increase the probability of every single action we just took. But that seems like a bad idea because some of the actions were good and some of them were bad. About half of them were good and half of them were bad. So the idea behind the baseline is we want to only increase the probability of an action if it was better than expected. So only about half of the actions were better than expected, so we should only increase the probability of the good ones. So now instead of just multiplying grad log probability by the sum of following rewards, we do the sum of following rewards minus some baseline, where the baseline was the estimate of, what will turn out to be a good choice for the baseline is the expected return before taking that action. So one nice fact is that for any choice of baseline, the gradient estimator we get is unbiased. I won't show the derivation in this slideshow, but it's pretty easy to derive by just looking at, it turns out that if you take the expectation of grad log probability, where we're sampling from pi, this expectation comes out to 0. And you can see that, that's sort of a well-known fact, and it's easy to derive. So any choice of baseline that we plug in here is going to not introduce bias. And it turns out that a near optimal choice to plug in here is just the expected return, conditioned on the state, S sub t. And intuitively, that's because we only want to increase the probability of action t if the returns that you got here were better than expected. So that means we should plug in the expected return here. Actually, it turns out that this isn't the optimal choice that minimizes variance. The optimal choice actually involves some kind of weighted estimate of the return. But as it turns out, it's near optimal, and it's as good as, for all practical purposes, it's the best you're going to do. And you can also, another way to derive this is to just write out the formula for the variance. So the variance of x, of some random variable x, is just expectation of x squared minus the expectation of x squared. So if you write that out and you make some approximations about things being independent, then you'll find that you just want to minimize the expectation of this term squared, of sum of rewards minus baseline squared. So that means you should just take this baseline to be the mean of this quantity, or the best possible estimate of this quantity. So that's a very useful and powerful variance reduction technique, and that'll get you a lot of mileage in practice. The other technique that gets you a lot of mileage is to introduce discounts. How am I doing on time, by the way? Does this session actually end now in 10 minutes? Okay. Okay, good. I'll finish up in the next 10 minutes. Okay, so the other method that's going to give you a lot of mileage is to introduce a discount factor. So far I haven't added any discount factors, as I said before, I've been talking about the episodic setting, where you just care about the sum of rewards over a whole episode. Sometimes, if you read reinforcement learning books, you'll see a different kind of problem setting where you're actually optimizing a discounted sum of rewards. And I think this is a reasonable thing to do, but often the time horizon you care about is very long. So, for example, you might care about, well, in these Tetris, that Tetris benchmark I was talking about earlier, the game might take 1 million time steps. So that means if you want a discount factor that actually includes all those time steps and counts all of them, it would need to be 0.999999, right? So anyway, what the discount factor is it downweights the effect of future rewards. So I didn't explain in reinforcement learning textbooks. What you sometimes see is you care about the sum of reward times r sub t times gamma to the t. So the problem with that is that that's basically going to ignore all rewards that are far into the future. So I think that this problem setting doesn't usually make sense, and I think it makes more sense to think about the discount factor as a variance reduction parameter, or it's at least in the policy grading context, what it does is it gives you a bias variance trade-off. So what we can do, so the way we're going to introduce the discount factor here is we're going to modify our previous formula for the policy gradient by introducing the discount factor. So recall that our previous formula, what we have is sum of rewards minus baseline. So here we're just going to modify it to be sum of rewards multiplied by this discount factor minus baseline. So this discount factor, you can see that the discount factor is measures the difference in time between this reward and the action you're looking at. So it's based on the assumption that the action only affects rewards in the near future, but after that, the effect of this action is washed out. And it's not going to, basically we can measure whether this action was good or bad by looking at the next, by looking at some short horizon after the action. But the system kind of forgets the effect of that action after a while. Okay, so if we use this discount factor, then if we want to, then by the same arguments I was providing before, we want the baseline to be the expected discounted sum of rewards, so that we can maximally reduce variance. And the way you can also think about this discount factor as it's doing credit assignment by assuming that the action deserves no credit for rewards that are far into the future. So if your discount factor is 0.99, then 100 time steps later, you've reduced, you're sort of downweighting everything by a factor of 1 over e, and so on. So that's the idea of using this discount factor. And now it's just worth looking at the formulas we've shown so far, and one way to interpret them is as multiplying grad log probability times an estimate of the advantage function. So I haven't defined the advantage function yet, but you can think of the advantage function. But here, what I mean by this is that the advantage estimate is just telling you whether the action was good or bad. So we're just multiplying grad log probability times some scalar, which is an estimate of whether the action was good or bad. And in this case, we're just taking that scalar to be the discounted sum of following rewards minus a baseline. Okay, so putting everything together that we've shown so far, what we get is this so-called vanilla policy gradient algorithm. And so the way this works is iteration, first collect a set of trajectories by executing the current policy. Then at each time step, we compute the return, the discounted return, which is this sum of future rewards downweighted by discount factors. And we compute the advantage estimate, which is defined as this return minus the baseline. Then we refit the baseline by this is just a nonlinear regression problem, so we can set up a least squares optimization where we fit the baseline to the returns. And then we update the policy by taking a policy gradient. We compute a policy gradient estimate, which is the sum of terms of the form grad log probability times advantage. And actually, there's a slightly modified version of this, which is sort of a more modern version, which is compatible with very efficient implementations, is what's called the advantage critic algorithm. So there's this paper, Asynchronous Methods for Deep Reinforcement Learning, which introduced what's called the asynchronous advantage actor critic algorithm, A3C. So that's so the asynchronous part doesn't really matter here. It's just sort of for performance reasons. But for what I'm presenting here is what could be called the advantage actor critic, which is sort of the vanilla policy grading algorithm, but with some like modifications that make it more compatible with efficient implementation. So the way it works is now instead of collecting full trajectories, you collect a set of a certain fixed number of time steps for each update. So you have your agent and it acts for t time steps, such as 20 time steps, and then for each time step along that trajectory segment, you compute the return, and where you cap it off with the estimate of the value function at the end of the trajectory, and you compute the advantage function also at each time step. And so we're going to use the return as the target for the value function in a regression problem. And value function is synonymous with baseline if you're not that familiar with it. So V here can also be thought of as the baseline B that we were using in the previous slide. So here we're going to use R as the target value function and A as the estimated advantage function. And we just set up a loss function which has our policy gradient loss, which is grad log probability times advantage, and then also our value function regression error. And this can be plugged into a stochastic gradient algorithm such as that. So this is exactly the same thing we were doing before, but it's just this is just a version that uses a fixed number of time steps at once instead of collecting full trajectories. Okay, so that's, and even though this is very simple and basic, it's, when you run it for a really large number of time steps, you can get pretty impressive results, such as navigating a 3D maze, just learning a policy, which is a convolutional neural network, which navigates the 3D maze using only pixels as input. So this was from DeepMind about last year from Vlad and me and collaborators, and I have a video actually of that. So actually I'm out of time now, so I just want to show a couple videos just to sort of show what you can do with these methods. So I'll show the video from the A3C paper, which is navigating a 3D maze using pixels as input, using exactly this algorithm. And I'll also show a video of, so I didn't get to this part of the presentation, but you can also, there's also some methods you can do to get more information from the data you collect, and also regulate your, so you can do a better update where instead of just doing a gradient update, you set up a trust region problem and you solve that. So you set up a little constrained optimization problem and you do an update on that, and you end up getting better sample efficiency and also sort of more reliability. So I'm not going to What? Oh yeah, so I'll show the first video, and then so that's labeled 1-A3C, and then the last, and I also want to show the video that's T-PPO, which is sort of, or actually show 2-TRPO, which is learning to run in simulation, which is based on this trust region kind of algorithm, which I didn't have time to talk about. So yeah, please show the first video. Okay, good. And then once that's done, start the 2-TRPO video. I can't see what you're showing, so just tell me when to start. Okay, cool. Okay, so this is a video that my collaborators and I were working on learning locomotion controllers where from scratch, where you just have this robot in a 3D physics simulator. The input is just the joint angles and joint velocities and so forth, and the output is the joint torques. And so it's a pretty low-level representation of everything. And it starts off just falling over instantly, but eventually it starts falling over a little bit more slowly, and so on until finally it's actually running, and it can actually run indefinitely long after learning is complete. Then there's nothing in that algorithm specific to running, so you can also use it on a four-legged creature, and you can also use it on learning how to get up off the ground. So we defined, I don't know if we've gotten up to that part yet, but we defined a reward function, which is something like distance of your head from some target height. And then it'll learn how to do some kind of ballistic motion with its arms and get up off the ground. And so people have previously learned locomotion controls. So we weren't the first people to do that, but previous attempts have usually used much more hand-coded representations where you specify, for example, that you're trying to place your feet left, right, and your network is just determining where to put your foot, for example. Whereas we just had a feed-forward network mapping from observations to actions directly. So this was a video produced by my collaborator recently, where it's just like using. So basically, you've got this guy running around and being hit in the head by bricks, and he still manages to get up off the ground. And he's running towards the red balls. So you see these red balls randomly appearing. So here, your reward function is not just to run forward, but it's to run towards the ball, and the balls randomly appear. So I mean, when you see this, I think it becomes more plausible you could actually get robot soccer, or football, sorry, or something, if you really put these skills together. So I'm pretty excited about what we can do with that. That's using something called, we call it proximal policy optimization. It's basically, it's like trust region policy optimization, but you use a soft constraint instead of a hard constraint. And actually, I'm going to put out a paper on that in the next week or so you can check out. So it'll be on the archive in a few days. Yeah, I wish I could tell you about more of this stuff, but we're out of time, and it's late over there. So hope you all enjoy your evening.